Today we're going to discuss spontaneous reactions and the conditions that favor those. Spontaneous reactions are reactions that occur without influence. That means that you don't have to make them happen. They're going to happen on their own accord. Nature actually favors some conditions over others. It actually prefers exothermic reactions because those are reactions that are going to be losing energy. That way energy doesn't have to be added for it to happen. So whenever you see that delta H is negative or a reaction is exothermic, it's going to be favored by nature. This can also happen with phase change since they are losing heat in the reaction. Examples would be water freezing. So at its freezing point, it loses heat all on its own. Or when water vapor condenses, that would also be an example. Or, and you may have discussed this in lab, water can deposit. Other gases can do that as well, but that's when it goes from a gas directly to a solid. And you saw that with the iodine lab. The other condition that nature favors is increased entropy. Entropy may be a new term for you, so I want to talk a little bit about entropy. Entropy is a measure of disorder or randomness. So nature actually favors disorder. The universe tends toward chaos at all times. So when mom tells you to go clean your bedroom, I suppose you could say, well, but that's not what nature wants. Nature wants chaos. And where we see order in the universe is where we look for life, because biological systems tend to create order. And that's probably why mom wants you to clean your bedroom. So examples would be melting, because you're going from very ordered molecules to ones that are less ordered in a solid, or from a solid to a liquid. So melting. Also boiling then, going from a liquid to a gas, much less order in a gas. Or when you skip that middle phase and you sublimate, well, we don't, but when something sublimates. Or another example, which we couldn't do when we talked about exothermic, but is dissolving. So you take maybe, think of salt and how ordered those crystals are, and you stick it in water and they become very disordered. And I put this on here and I didn't say it, but we show a change in entropy as delta S. S represents randomness. So nature favors a positive delta S and a negative delta H. If we were to look at the conditions of a reaction and find that delta H is negative and delta S is positive, it will always be spontaneous. However, if delta H is positive, so it's an endothermic reaction, and chaos is becoming less, or delta S is negative, so it's becoming more ordered, it will never be spontaneous. Never. A lot of energy is going to be added into that. Think about when mom sends you to your bedroom. It's not like your bedroom becomes clean and orderly on its own. You have to put a lot of effort into that. However, I bet you don't have to put much effort into making it a mess. I bet it does it all on its own. Now, sometimes you'll find the conditions where delta H and delta S are both negative. And delta H being negative is going to be favorable, but delta S being negative isn't. So it really kind of depends on the temperature where this reaction is occurring in order for this to be spontaneous or not. And the same thing's true when delta H is positive or it's endothermic and it is becoming more disordered. So for these two, we can lump them in together. When the signs are the same, it really depends on the temperature if it's going to actually be spontaneous. They typically don't ask about those on the exam. It's the ones that we discussed up here. When it's exothermic and becoming more random, it's always spontaneous, where the opposite conditions, where it's endothermic and becoming more ordered, it is never spontaneous. So let's look at some of these and see if we can determine if they're endo or exothermic and what's happening to entropy. So we have calcium solid becoming calcium liquid. In order to make it a liquid, did we have to add heat or is it losing heat? So we have to actually add heat in order for calcium to go from a solid to a liquid. And when we add heat, that means that it is endothermic. Now, to determine the entropy or the chaos or randomness of the system, when we're going from a solid to a liquid, is it becoming more chaotic or less? Well, it's becoming more chaotic, so we have an increase in entropy. So the next 1, 2, 3, 4, 5 examples are all similar to this. So I'm gonna go ahead and fill those in. What I'd like you to do is pause and attempt those questions on your own, and then play it again to see how well you did. All right, hopefully you did well on that. Those were all examples of phase change. But now we need to look at examples where there are actual reactions. These next two are going to be in Table I, and they're actually just dissolving, but each of these ones actually involves some heat in the reaction, which is why you're going to find it in Table I. I'm not going to pull up Table I for you right now, but I am going to look up the values, and these ones are near the bottom. The last, 7 or so are all examples of dissolving things in water. So KNO3 actually has a positive delta H. You guys did this in lab, and since it's positive, that means that it's endothermic. And then to look at the chaos or randomness of the system, you're going from a solid to aqueous particles. So we're actually increasing our randomness. The next one also in Table I, it's right below that one, and you also did this one in lab, and delta H is negative, so it's going to be exothermic. And again, this time, you're going from a solid to aqueous particles, plural, so we're actually increasing our randomness or disorder in the system. Next one's just a phase change. To go from a solid to a liquid, you have to add heat to it, so it's endothermic. And it is becoming more random going from a solid to a liquid. The next one's also in Table I, and it is a negative delta H. It's exothermic. When it's not just a simple phase change, you're going to have to look at Table I and then look at the sign. And now looking at the randomness of the system, we're actually going from particles in solution to a liquid. And you probably are thinking, well, gee, it's just going from being a liquid to being a liquid. But you're going from multiple particles distributed through an aqueous solution to just a liquid sample of water. So we're going to say it's going to decrease, less particles floating around. Next one again is just a simple phase change, going from a gas to a solid. It would be losing heat, so it's going to be exothermic. And we're going from a gas to a solid, it's becoming more ordered, so entropy is going to decrease. And then the last one, this is a reaction. Notice it's not just a phase change. We do have multiple reactants in a single product, so we're going to look in Table I. And in Table I, you're going to find that reaction. Be very careful you're looking at the phases of matter and the coefficients to make sure that you've got it all matched up, because there are a couple that look very similar. This one is negative, so it's exothermic. And since we're going from multiple gases to a single liquid, we're going to say that our chaos is decreasing. It's becoming more ordered. So let's look at some of these. First one, we have a phase change. We're going from a liquid to a gas. Delta H, would we have to add heat or would we lose heat? Well, we're going to add it, so the sign on delta H will be positive. And then delta S is the chaos increasing when you go from a liquid to a gas. And yes, it is. So we're going to put a plus on that as well. So will this reaction occur spontaneously? We're going to say, well, when the signs are the same, on the front of the notes we said that really depends on temperature. So we'll just write depends. Water freezing, that's going to be losing heat, so delta H is negative, but it is becoming more ordered, so we're losing chaos. So again, signs are the same. The spontaneity depends on temperature. Carbon dioxide depositing, so it's going from a gas directly to a solid. It's going to be losing heat. And going from a gas to a solid, we're actually going to be losing chaos as well. So this one's going to depend on the temperature. TNT exploding is going to be releasing heat, so that's exothermic. And it will create more chaos, so that's gonna be positive. So this one, with it being exothermic and increasing the chaos, we're going to say that that is spontaneous. Now obviously there must be some activation energy or TNT would explode on its own all the time. Sodium chloride dissolving in water. So sodium chloride dissolving in water you can find in table I. It's the third one up from the bottom. And delta H is positive. And it is becoming more random. So this one again depends on temperature. All right, at this point you should be pausing this and I'm going to fill in the rest of this and you can check your answers. All right, so here's the answers to the last few. Some of these, it might make it more obvious why we say it depends on temperature. If we look at number 10, chocolate melting, it does require heat and it does increase the chaos. Chocolate will, however, melt on its own if you get it warm enough. So that's why we say it depends on the temperature. So it depends on the temperature where the reaction is happening. And then this last one, cleaning your bedroom, obviously you have to put in a lot of energy. It is endothermic, and you're actually creating order, so you're decreasing the chaos of your system. So this will never be spontaneous. It goes against the laws of the universe.